So what we're going to do today is we're just going to go through and do the ranking exercises. So I will share my screen, and in OneNote, under Energy, under Class Time, it says Class Time Friday, and there are a bunch of ranking exercises. I would like you to work through them in order, okay? And then I'll stop you periodically and we'll go through them or talk about them, okay? There may be a dog eating my pencil case, which is not allowed. So you guys get started on that. I'm not going to record that part, but then I'll check back in with you in about 5 or 6 minutes, and we'll see where we need to be. We'll start talking about the first one. Okay? Good? Yes? Okay. Then I'm going to resume recording. I'm going to share my screen. Okay. So, a cart with a spring plunger runs into a fixed barrier. The mass of each cart, its velocity just before the impact with the barrier, and its velocity right after the collision are given in each figure. Rank the work done by the barrier on each cart from greatest work to least work. So, what do you think? I know I didn't give you the little greatest, the little things at the bottom to rank them by, but which situation or situations is the greatest amount of work done?
D?
I'm sorry, what'd you say again, Dagny?
D?
D? Why do you think it's D?
Yeah. Well, because I was looking at work as like the kinetic energy of the first minus the kinetic energy of the second.
Well, it should be the other
And
way, right? The kinetic energy of the final minus the kinetic energy minus the initial.
never mind. Then
I got E and F to be the greatest. They both had 0, and I got the other values to be negative.
Okay. So does anybody agree with Lauren? Sophie says yes. She's with you there. How about my other Zoom friends?
yes.
Yes? Okay. Sounds good. All right. So Lauren, did you do it by using this equation? Work was the change in kinetic energy?
Yes.
Okay. So then what comes next?
I replaced the kinetic energy final and initial with 1/2 NB squared.
Oh, no, I'm sorry. I mean, which was the next set of the ranked?
Oh, sorry.
Okay.
I had B, C, and D.
We're all the same.
Together.
And then A was left over?
And then A.
Okay, and Annabelle was right there supporting you. So are we good with the first one? All right, sounds good. And we're still working on the second one? Okay, about how much more time do you think you need? Couple minutes? Okay, all right, I will give you a few minutes then. Okay, are we good with the second one now? Sliding masses on an incline? Lauren, Tia, are you done with that one? Almost? Okay, take another minute. The rest of you keep moving. Okay, so you want to know which ones have the greatest kinetic energy when they get to the bottom, and they all start from rest. So again, we would go from greatest to least. So who wants to try this one? Who wants to give us the one that has the greatest kinetic energy at the bottom? Or how about, oh, go ahead, Eva. What do you got?
Oh, I did F.
Okay. And then what?
A and B.
Together. Good. And then?
C, and then D, and then D, and then
E. Okay. Do we agree? I get some thumbs up. How'd you do it, Eva? Can you explain?
I just did U equals MGH.
Okay. Hang on, let me get back to my pen here. So you assumed that at the bottom here you had UG equal to 0, right?
Yeah.
Which meant that all of the UG up here became kinetic energy at the bottom, right?
Yeah.
Okay, so it was pretty much just saying 1/2 MB or MGH, right?
Yeah.
Okie dokes. Was there a question? Are we good on this one?
Dr. Goetz,
Yes.
could you have done work equals Fnet dot D, which equals the change in kinetic energy? It was more complicated, or it was kind of weird, but I found I split FG into the X and Y components and then dotted them with the heights and the length of the ramp.
Yeah, and then you had to find an angle, and yeah, I guess, but I think, and I would be a little careful there because in this, well, it works because you're saying that the work is equal to the change in kinetic energy, and you're also saying that it's equal to the negative of the change in potential energy. And that only works because it's a conservative force.
Okay.
So I don't think there was anything wrong with what you did, but I think there was A, an easier way, and B, it only worked because you were only dealing with a conservative force. Okay?
Okay, thank you.
Sure. All right, are we ready to talk about number 3, or do you still need more time to work on number 3? Dagny's good on number 3. No, we still need more time? Okay, then take a few more minutes, and I will pause my, share my screen. All right, so what we have here is a graph of velocity versus time for an object that moves along a straight horizontal line under the perhaps intermittent action of a single force exerted by an external agent. So we want to base or rank this from greatest to least on the work done on the object. Okay, so how'd you do it? Somebody be brave. Talk about your process.
I can do that. So if we need to determine the work. So the work equation is Kf minus Ki.
Okay. So then what did
So
you
for
do?
that,
Go ahead.
we need to compare, okay, and then we need to compare the final velocity and the initial velocity.
Because we know that, right?
Because
so
yeah, and you just look the slope of the line, and for the greatest is B and G, I think.
oh, okay. So you want to, okay, you want to look at the slope between V initial and V final. Okay.
Yep.
All right.
It is.
It'll work, but it might give you an errant answer. Okay. Because I think that if what you're looking at is the slope, then what you're really looking at is this. Right?
Mm-hmm.
Because the slope of a velocity versus time graph is going to give you acceleration. So you're going to have to like figure out the acceleration for each of those intervals and then multiply it by the amount of time. I don't know if that'll work. I don't know. You want to talk some more, Fiona?
I think it's complicated and like I might got some error, so no.
Well, I would kind of go back. I think you can do it from here, but I think it's going to be more complicated. Okay. Did anybody look more at the change? Lauren, you want to talk about how you did it?
I just wanted to add that I looked at the slopes of the graph like Aaron did also, but instead of the slope, I just looked at the initial value and the final value
Mm-hmm.
of the velocity,
Mm-hmm.
and then plug that into the equation.
Mm-hmm. You could say that the amount of work done is proportional to the final velocity minus the initial velocity, as long as you like took the absolute values. Or you could square them, either way.
Right, right.
Mm-hmm.
Oh, I didn't do the absolute values.
Well, but remember that when you're looking at this equation, those velocities are squared.
Right, right. Okay.
So
I think that's what I did. I just looked at the final and the initial values.
okay. So let's see. Fiona thought that B was the greatest. What did other people think?
I also said B.
Okay. Lauren, is that what you got too? Yes. Okay. And then what? What comes next?
I did G is my second value.
Okay. What do other people think? Okay, Lauren agrees with G.
But it is B and G is equal?
No.
Or no?
No, they are not equal. Because the velocity here is 2 and it's 6 here. It's -2 and 3 here, so the slopes aren't the same. And that's why I was a little concerned, Fiona, that you might end up with some errors when you did it that way. So no, B and G are not equal. And then what?
I had E after that.
Okay, what do we think? We agree with E? Yes, no? Yes, no? And then what?
A and F are equal.
What are equal?
A and F.
Okay, and I think D too. Right? Because there's no change.
Oh, I didn't see D, sorry.
Yeah, it's okay. All right, but A, D, and F will be together. And then what?
Then
What's
C.
left? C. Okay. So I really think that the way to look at it is to kind of focus on that change in kinetic energy and just pretend that the mass is equal to like 2 or something. Okay. And then just figure out what that change in kinetic energy is from the beginning to the end of the interval. Are we okay with this one? Yeah? Okay. What about the last one? Do you need more time? I see a couple nods. Okay. Then I will give you, I'm going to pause the recording. I'll give you okay. Let's talk about the last one here. All right. I'm going to share my screen. Okay, so we've got our pendula here, and we want to know what the maximum speed will be at the bottom. So how are you going to figure it out? Anybody got any ideas? What were you?
It is released at the rest.
Yes, it's released from rest.
So it should be, it's just have the final velocity, could I say that?
Sure. So we're going to say that
E
Emac initial is Emac final. K initial plus UG initial is K final plus UG final. Did you make some assumptions about some of those, Fiona?
Yep, KI is 0 and UGF is 0.
Okay.
So I just write down the equation for the velocity.
Okay. What do you mean the equation for the velocity?
I say V equals to radical 2GL times 1 minus cosine theta.
Okay. So let's back up in case people forgot about that. So we've got 1/2 mv final squared is going to be mgh. Okay.
And where
So let's just look at C for a minute. And if we say UG is equal to 0 down here, then this is our height. But remember that this whole distance here is 4 meters. And if this is theta, and we talked about this yesterday, then remember H is L minus L cosine theta. So that's the formula that Fiona was talking about. But remember that theta is the same. So we've got MGL, 1 minus cosine theta is 1/2 m v f final squared. and our masses cancel, and this part is constant. So basically we're saying that V final is proportional to L. So the longer the bob, or I'm sorry, the longer the pendulum, the greater the velocity at the bottom. Okay, we good? All right, then I'm gonna stop this part. I'm just gonna look at my planner. I know that we are at 2:20. No classes on Monday for anybody, and that's our drop day. Tuesday, we're gonna do conservation of total energy, but you should have already read about that. Wednesday is a Monday schedule, and we've already done, and we don't have class on Monday. So no classes on Wednesday, no class for us on Wednesday. We have the test on Thursday, and then on Friday, we're gonna do a little Hooke's Law Lab, okay? And I will grade the homeworks over the weekend. I'm almost done with grading the homework number 3, but I will get those done over the weekend so that you can study from them for Thursday's test. Okay, and that test only goes through the conservation of mechanical energy, which is what we finished yesterday. Okay, all right, great. I'll see some of you in a little while for AP Calc. Bye.